Hello and welcome to this lecture 5 of the course Basics of Semiconductor Devices and Technology. In last 4 lectures we reviewed basically the origin of semiconductors, or we reviewed the history of semiconductor devices and technology, and we also reviewed the origin of quantum mechanics. In the last lecture we tried understanding some of these fundamental experiments which were done, which led to the birth of quantum mechanics from some numerical problems point of view, and we tried solving those numerical problems to get a better insight into the origin of quantum mechanics. And in today's lecture we are going to basically talk about the mathematical formulation of quantum mechanics. Primarily we'll look into the Schrodinger wave equation, and we'll try to make some sense out of it. So often the question comes is, what is quantum mechanics? I mean, what do we do with this? As we discussed in the previous lectures, that Bohr's theory could not explain everything. We had these several experiments done. We got some ideas about the quantum or the quantized behavior of aspects at the microscopic level. We understood that things which are, let's say, microscopic in nature, they follow a wave particle duality principle, which means every particle has a wave nature, and a wave also behaves like particle. We saw that there is an uncertainty principle linked to, for instance, observation and measurements at the microscopic level. We also saw that some numbers were produced by Bohr in terms of the hydrogen atom radius, and we found that those numbers are probable but not accurate. So many of these things and the questions led to the question that how do we predict behavior at a quantum or at a microscopic level? At the classical level, for the macroscopic world, we know that the behaviors are very well predicted, or the dynamics of a system, dynamics of an object are very well explained or predicted using Newtonian mechanics or the classical physics, right? If it is very heavy objects, or if it's about objects moving at the speed of light, again we have relativity theory, and many of the aspects of those macroscopic world can be predicted. The question often being asked during that time was, if there is a way by which we can predict the dynamics of microscopic world where everything looks probabilistic, where everything looks uncertain. And this in quest of this, Schrodinger, then subsequently Heisenberg, and other people like Max Born and Paul Dirac, they came up with this mathematical formulation. And collectively this mathematical formulation and the understanding that people developed, or the implications which people developed, that understanding or the implication is what is called quantum mechanics, right? So let's move forward. Before we get into the Schrodinger wave equation, which is, I would say, the most fundamental equation, or the founding equation, or the most important equation of quantum mechanics, let's try to understand the wave nature of objects and wave particle duality in a little better way. You remember one of the numerical problem that we solved, where if you take an electron, keeping in mind the electron mass, you remember the relation between wavelength and the momentum. They are inversely proportional. So which means wavelength is inversely proportional to the mass, right? This is an equation that we looked into in the previous class. And so based on that, if we try to extract the wavelength of an electron, what we get, this is of the order of an atom, or in fact the wavelength associated with an electron is much bigger than electron itself. So if you say this is an electron, then the wavelength associated with that is much bigger than an electron. However, if you take a macroscopic object, let's say a human body or any other macroscopic object, right, and you calculate the wavelength associated with that, you find it falls somewhere in the range of 10 to the minus 33 to 10 to the minus 36 meters, and this is a number which is far smaller than the macroscopic object that we are dealing with. So if this is the macroscopic object, the wavelength associated with that is so tiny that you cannot experience that wavelength. Please ignore that. Yes, so I was saying that the wavelength associated with that would be so tiny that you cannot experience that wavelength in conjunction with this macroscopic body. So when it comes to wave particle duality, the wave particle duality is valid for every single object, every single particle in the nature that at least the humans are aware of. However, this becomes relevant when the mass of the particle we are dealing with becomes much smaller, and then the size of the particle we are dealing with is much smaller, and in that case the mass or the size of the wavelength itself would be bigger than the size of the particle. Whereas if it is about macroscopic world where the mass is noticeable, mass is observable by classical means, the wavelength associated with that would be much smaller than it cannot be noticed in context of that macroscopic object. Now, often the question comes is that what is that wave that is associated with an object, that particle? I mean, we often know waves as, for instance, sound waves, which are mechanical in nature. That's nothing but the vibration of the molecules or the gas molecules around, and when you speak something or when some vibrations are produced by a sound producing device, then this vibration is transferred to neighboring molecules, and from these neighboring molecules it will be transferred further, and that's how the sound wave is propagated. So this wave we all know is sound wave. You also know there's water wave. For instance, you have if you drop a heavy object or a body in a water body in a pond or something, then you will get these water waves produced around that point where the object is dropped, and the water waves are also propagating. So for instance, if you take a cross section, it may look like this. It may be propagating, and at a certain time you see this has shifted, and so on and so forth. So these are water waves. And you also know you have light waves. For instance, you can have electric field in one direction, you would have magnetic field in the other direction, and the wave would propagate in the third direction. So this is the electromagnetic field or the electromagnetic wave that we are aware of. Now the question is, what is this wave that is associated with these macroscopic or microscopic objects? So to understand what is this wave, let's try to take an analogy. Let's say you have you tie a string between 2 points, and now this string is in ground state, so you can call it n equals to 0, where there is no vibration across the string. Now you hold the string somewhere at the center, you move it down, you deflect it, so it will look something like this, and then you leave it. So what will happen? There will be a vibration along this string, right? And this string will go up and down, right? So it will vibrate up and down like this. So this is one way of vibrating the string, and there can be different ways of vibrating the string. So for instance, if you hold it somewhere here, you pull it down, you vibrate it, now you get some kind of a displacement, and then gradually you will notice that there's a vibration which exists across the string. And if you assume that there is no damping in the vibration across the string, which means there is no loss, I mean, what you are doing is you are transferring energy to the string and you're leaving it, and then this energy translates into these vibrations, right? And if you assume that there is no loss of energy, then the vibrations will continue, and depending on how much energy you transfer or how much deflection you produce, and depending on the length of the string, you will have different rate of oscillation. So if you measure, depending on the energy that you transfer, you may have a certain number of oscillations being present, and these will be seen as standing waves. Now from this you can measure the wavelength of these oscillations. So this wavelength will reduce, or the frequency will increase, if the energy transferred is increased. Right? This is something which all of you would have experienced, all of you would have noticed while playing with these strings, maybe in your childhood or high school times. So you can think of these electrons as these standing waves, as a cleaner picture is drawn here. And these standing waves would be these oscillations of the string along the reference point, and the number of cycles that you get is equivalent to the amount of energy associated with these oscillations. Now in case of electrons, if we talk about electrons, these standing waves would be in form of a circular standing wave. So for instance, I mean, we are talking about bound systems. So let's again go back to these standing waves. So how do you get these standing waves? Because we are talking about a bound system. There's no way where the energy can produce outside. So since the energy is not producing outside, and since the energy is not being lost in the system, I mean, for instance, we are assuming that these boundaries are ideal and no energy is transferred at these interfaces, and we are assuming that there is no frictional force here, so there is no energy being transferred to the ambient, and there is no damping. And as you can see that this is a string in the bound state, and that's why you have these standing waves being formed there. Similarly, an electron is in a bound state. Electron is orbiting around the nucleus because of the electrostatic force of attraction which is present there. So you can say that this electron is present in a bound state, but it's a circular bound state. And you can think of this wave as these oscillations or these standing waves being present along the line of, or along this orbit. So you can think of this wave associated with the electron as these kind of oscillation. Again, these are all interpretations. Keep in mind. Now let's see, what does it mean in terms of energy. For instance, you remember Bohr's model, where you have these different levels. You have n equals to 1, n equals to 2, 3 and 4. That doesn't mean that this level is far apart. I mean, though from quantum mechanics, if you calculate, you actually find that these levels are a bit apart from, or the radius from the center to this level to n equals to 4 is different than n equals to 1, but in principle these are all energy states, or states defining the energy of the particle. So now if you think of from the Bohr's model point of view, if n equals to 4, what we are saying that they are, this is lambda equals to 4, or there are 4 cycles being present for this electron, which is forming a standing wave in this bound fashion. I mean, in this circular fashion. If it is n equals to 5, you have 5 lambdas being present in this circular orbit. I mean, this is 4 lambda being present in this circular orbit. If n equals to 6, it is 6 lambdas being present in the circular orbit, which means it has got 6 cycles in this orbit. If it is n equals to 7, it has got 7 lambdas or 7 cycles in this orbit. Now what does it mean? If you go back and if you try to understand this from this classical analogy that we developed, when it's 4 lambda, it corresponds to a certain energy. Let's call it E4. When it is 5 lambda, it corresponds to certain energy, let's say E5. It is 6 lambda, it corresponds to certain energy, let's call it E6. And in this case, let's say this is E7. And now this is E7 greater than E6 greater than E5 greater than E4 and so on. So this is the representation, this is the analogy that you can develop from this classical picture and think of what is wave interpretation for electrons. Now obviously, when we say that these are standing waves and the electron is revolving, what does it mean is that electron, there's one electron, for instance, right? And so you can think of this, that electron is present somewhere in this orbit, and this wave is representing the region where the electron could be present. So this wave in some sense is basically telling you the probability of finding, or the region where the possibility of finding electron is finite. And again, we'll look into that later on, that how do we interpret wave and its amplitude, and how do we correlate that with the probability. So again, using this, the Bohr has given this model. So what does it mean? That a higher value of n corresponds to higher oscillations, and higher oscillation means more number of cycles, and that's the lower wavelength, and that means higher energy. Now so from here you understand that if this in principle, if this radius or if this orbit diameter is increasing, you won't get lower wavelength for higher number of cycles. So in principle, they all are in the same region, maybe slightly different in terms of the actual distance from the nucleus, but this is not really like a planetary system where something which is in n equals to 3 orbit will definitely be far away from the nucleus. Though quantum mechanically, when we calculate, we find that that's certainly far away from the nucleus, but that finding is based on the quantum mechanic principle and the solution of the Schrodinger wave equation, not based on what Rutherford had presented. So now again, we come back to this question: what is quantum mechanics? And as I said, that quantum mechanics is nothing but the interpretation of all these aspects at the microscopic level, and the understanding that people developed using the mathematical formulations produced by the people I named earlier. And there are many interpretations. There has been many thought experiments on that, many counter arguments, counter arguments, and based on that there are many interpretations. For instance, there's Copenhagen interpretation, many world interpretation, quantum decoherence, and Bohmian mechanics, and so on. What broadly we are going to follow will be the Copenhagen interpretation. So as I said, there are again different ways of relating the wave nature or wave function to experimental results, and our fundamental understanding, beliefs about the nature. I would like to quote the following things, and the two different views. For instance, Einstein, in one of the discussion with Bohr and other people, said that God does not play dice. It's a very famous statement, and in response to that, Bohr said, but still it cannot be for us to tell the God how he is to run the world. So you can see that there are two different worlds, and quantum mechanics is still successful, it's still valid. So that's the reason why we'll continue discussing this. So now we come to the Schrodinger wave equation. We'll discuss this in detail, but I wanted to start by showing you what this equation is about. And often this question comes is that how was it derived, how was it found, how was it discovered? And this was a question which was often debated and asked during in older times as well. And for instance, once Richard Feynman was asked that how Schrodinger wave equation was derived, and his response was, it's not possible to derive it from anything it just came out of mind of Schrodinger. So that's what we will try to do here, and we'll try to make or develop an understanding using this equation. And there are different ways of understanding it, and we'll also see that what mathematically once we have understood things, then we will see how to reverse engineer and we'll derive it. As I mentioned earlier, that Schrodinger equation is the most fundamental and important equation in quantum physics. which explains how quantum particles behave, or objects at microscopic level behave. If you want to know, for instance, dynamics of a particle in a quantum or microscopic system, you must be using Schrodinger equation. So for instance, for classical systems, for macroscopic world, we have Newtonian equations to understand the future behavior of an object or the dynamics of a system. Similarly, if you want to understand the dynamics of a microscopic system or a microscopic particle or a quantum particle, you have to use Schrodinger equation. Now, the way it is derived is, that it follows the rules of waves. As I said earlier, that the idea behind the Schrodinger wave equation was that there's a wave particle duality, and therefore the quantum particles must behave like wave, and therefore there has to be a wave equation, and the term which is often calculated out of the Schrodinger wave equation, which is psi, or the wave function, should be a representation of, or the wave representation of, that quantum particle, right? So as I said, that with every particle there's some kind of a wave associated, right? And this wave must follow certain boundary conditions. So let's say a particle like electron is treated as a wave, and this wave can evolve in space, both in space and time, but it cannot evolve randomly. There are certain constraints which the wave must follow, and those constraints are what the Schrodinger equation tell us. And so the question is, what are these constraints? So let's say, if you talk about Schrodinger equation, if I write it slightly differently, it would be, for instance, I h bar d psi by dt equals to minus h bar square by 2m del square psi by del x square plus v psi. So for instance, if I rewrite this wave equation, this is what it is, and what it is nothing but the left hand side equation. The left hand side of the equation is total energy over time, and this must be equals to the kinetic energy of the system or of the particle plus the potential energy. So you can think of it in this way, that Schrodinger equation is nothing but an equation which tells that the total energy must be conserved, and that should be equal to the kinetic energy of the particle plus the potential energy of the particle or the system. Right, so the total energy of the system must remain conserved, and that should be the sum of the total kinetic energy of various particles involved in that system and the total potential energy of that system itself. This is nothing new. You all know this kind of relation, the conservation of energy relation, and the Schrodinger equation is nothing but the conservation of total energy at the microscopic level. Let's say if you talk about the electron, if the electron is inside an atom, and if it is just there, that's the potential energy. If it is, if you give an energy, extra energy, it goes to higher energy states, that's the kinetic energy you have given to an electron. So now the whole idea of solving the Schrodinger equation, or the whole idea of the Schrodinger equation, is that this is an equation which set certain constraints on this parameter psi, which is called the wave function, which is the which is the function which defines this wave nature, and you solve this equation in such a way that this relation is conserved and the constraint is maintained. And while maintaining this constraint, by knowing the aspects of the system, you find psi. And if you know psi, if you get psi, then you can understand, you can basically extract various other aspects of the system. So now the question comes is what is this psi? I mean, the psi is often denoted as the quantum states. So for instance, psi tells possible states a system can have. For example, let's say for hydrogen atom, we know that there are several orbitals. In fact, the finding of these orbitals also come from solving the Schrodinger wave equation. So let's say we know that there are different levels, n equals to 1, 2, 3, 4, and then there are different orbitals like s, p, d, f, and so on. Question is, what does it mean? It means that hydrogen atom would allow an electron to exist in these states, and these states are nothing but unique solution giving different psi values. So unique psi values will give you different n, l, m, and n values, right? Different unique psi values will tell you that these are the regions, these are the conditions where an electron may exist in a hydrogen atom. In fact, you would see later that the orbital theory that we discuss often is based on the solution of hydrogen atom, and the same orbitals and all these numbers that we often talk about would be different, very different, when you talk about, let's say, an helium atom, right? So another aspect that you should notice here, that this state would strongly depend on the system we are dealing. What is that system we are dealing? The system, what is the aspect which is dependent on the system? The potential. This potential is dependent on the system. For instance, if you take an hydrogen atom, the potential is related to the electrostatic attraction between the electron and the nucleus. But if you take an helium atom, the potential would change, and it will be electron to nucleus interaction, the electron 1, the electron 2 to nucleus interaction, and then electron 1 and electron 2 interaction. So now the potential function would be different for an helium atom versus what it is or what it would be for an hydrogen atom. Similarly, depending on the system, the potential function would significantly vary. Right. So and now as the potential function varies, the solution of this equation, which gives you the psi, would vary. And if the behavior of psi is also a time dependent function, and if that is different in terms of time, then the energy that you get out of psi would also be different. We'll look into these aspects a little later. Okay, so we were talking about psi. Now, the other representation of psi, I mean, one representation, I said that these are unique. Psi will tell you unique quantum states which are available or present with a quantum system. The other explanation of psi, which was given by Max Born, is a probability explanation, or is a probabilistic view of where to find a particle. So psi alone will not tell you anything. Psi alone doesn't tell much, except that unique solution of psi or unique solutions that you get for psi will tell you those unique states. But when it comes to a physical representation or physical meaning of psi, you don't get much out of it. But of course, you can operate on psi, and we'll see that later, and you can get useful or meaningful aspects extracted out of that psi, which are related to the system. For instance, you can use psi for calculating momentum, energy, and so on. So as I was saying, that psi was presented to be or explained to be the probability density function, in a sense that the mod square of psi, which is nothing but the psi star psi, assuming psi is a complex number. So if you have a complex number and you take you basically multiply this complex number with this conjugate psi star psi, what you get is mod of psi square. So it was said that this mod of psi square is nothing but the probability density function. So if a relation looks like this, and let's say if this is the wave that is associated, then the probability density function would be something of this kind. So if this is psi, which means nothing, psi square or mod of psi square will tell you that this is the region where the probability of finding an electron is finite, and the amplitude of this mod of psi square will tell you the absolute value of the probability of finding an electron in a given space. This could be, if this is one-dimensional function, then this could be x. Now, there are certain aspects or certain properties of psi. So, for instance, if this is probability, or if psi mod of psi square is probability density function, then you know that the overall area under the curve, which is this parameter, must be equals to 1. Now, what does this mean? Often you will get a solution and the psi would not be a normalized quantity. So if it is not a normalized quantity, you are supposed to basically divide that by the mod of psi square, and that will give you, you'll see the normalization later on, and that will give you a normalized psi, and later on that normalized psi will be used. Now there are a couple of other parameters and other properties of psi, and these were these boundary conditions and the properties under which you have to solve this Schrodinger equation, and we'll see how these properties will become useful later on. So first aspect is psi must be continuous and single valued. This is very important. Psi must not be a discontinuous function. Psi must be a continuous function, and it must be a single valued function. So that will help you solving wave equation when you are solving the boundary conditions or applying the boundary condition for this partial differential equation. The differential of psi as a function of x, or maybe also as a function of y and z, must also be continuous and single valued. Another aspect is that as the x approaches plus minus infinity, or as x approaches the limit of the system, if you are dealing with a bounded system and there's no state being present beyond that boundary. For instance, let's say you're dealing with a infinite potential well, and the inside dimensions are length of L, and beyond L and 0, the potential is infinite, which means nothing can go or nothing can exist in that region which has an infinite potential in that region, right? So which means that this is the boundary. So now in this case, the boundary is from 0 to L, and the wave psi will not exist beyond that, which means at this boundary the psi must become 0. Similarly, if this is an unbounded system, then the psi must become 0 at plus and minus infinity. As I said earlier, that the psi must be normalized, right? So so for that you have to divide by the mod of psi square, and if you have to calculate the probability of finding particle between a given region, let's say x1 and x2, you can calculate the probability by doing this integral within the limits of x1 and x2, which is nothing but, let's say if this point is x1 and this point is x2, it's nothing but the area under the curve, right? If I draw it again here, if this is your mod of psi square, and if this is x1 and this is x2, this area under the curve is the probability of finding the particle between x1 and x2. Okay. So now the question is that, can we see if there is a way by which we validate whether this equation is valid, right? So what do? We basically start with any random wave equation. I mean, the most simplest form of wave equation would be a wave equation for a free electron. The wave equation for a free electron. But before that, from where this free electron wave equation comes, this is very similar to, for instance, the classical wave equation that we are aware of. In this, there are two parameters. It's changing with x, it's changing with time. So you have, for instance, a wave which is changing with x, and if this is at t equals to 0, and let's say this is point A and this is point B and this is point C, what does it mean? That it's changing with time, that after a certain time the A will go somewhere here, and it's moving further with x. So if it is t greater than 0, the A point has shifted further, and B and C and so on. So this is a function, this is an equation which is changing in terms of with both x and time, which is basically this wave equation. Similarly, we have the wave equation for free electron, which is a complex number, and this, if you solve this equation and derive this form, you can do it. So you will get you'll get both the terms. So this term will tell you the wavelength, and this term will tell you the omega of the wave. I mean, that the energy is related to omega equals to h nu. So nu is the frequency. This term will tell you the omega, and this term, which is momentum, which is related to the wavelength, so this term will tell you the wavelength of the wave. So let's, without getting into the derivation of the wave equation, we can use this wave equation and see whether the Schrodinger wave equation is valid for any random wave equation, or let's start with a wave equation for a free electron. Now, what does it mean? Free electron means it's a particle which is freely moving in free space. It's not bounded. Now, this kind of particle follows the energy relation, where E equals to half mv square, and in fact this wave equation is derived from this relation. So this is a free particle which is moving freely in all directions in a space, as well as it's varying with time. So that's why it's an unrestricted particle, and there's a finite energy and momentum associated with this particle. So let's see if we can derive or we can reverse engineer the Schrodinger wave equation out of it. So for doing that, there are a couple of steps that you have to follow. In the first step, you differentiate psi 2 times by x. So you have to calculate d square psi by dx square. And if you differentiate this equation twice, what you get is this term. Keep in mind that when you differentiate once, this factor will come out, and again you get psi, and again you differentiate and this factor will come out, and again you get psi. So this is you have anything which is e to the power minus x or e to the power x, what you get is again you will get e to the power minus x, and that's why you see that this term psi has come out once again, right? So if you simplify this and double differentiate it, what you get is negative of momentum square divided by h bar square times psi. You can rearrange this, and this will tell you the parameter momentum square psi equals to h bar square minus of h bar square d2 psi by dx square. Um, so what do we have? We have first equation, which is psi. We have the second equation, which is momentum square psi. Now let's differentiate psi with respect to time. So you remember that psi was both function of x as well as time. So you can differentiate this with time as well. And if you differentiate with time and you rearrange, what you get is minus of I E by h bar times psi. So you rearrange this, and this is your d psi by dt, and if you rearrange this rearranged form translates to this, which is E psi equals to minus h divided by I times d psi by dt. Now remember, negative of 1 by I is I, so we'll be rearranging this later. Now, as I mentioned earlier, that if it is a particle in free space which is moving with the speed much lesser than light, speed of light, then you can use the conventional energy conservation form, which is total energy equals to kinetic energy plus potential energy. Now, kinetic energy of a particle is nothing but half mv square, and we earlier saw that half mv square is nothing but this mv is momentum. So if you multiply this by 1 by 2, m square v square by m, and mv is momentum, so this becomes p square by 2m, right? So you feed this p square by 2m here, and we have then additional term, which is the potential energy. If it's a particle in free space, you actually know that there won't be any potential energy, but let's keep this potential energy for the time being in this equation. Now, if you multiply psi both sides, so if you multiply psi here, and psi here, what you get is equation number 5, which is E psi equals to p square psi by 2m plus u psi. Now let's see, we have E psi, which is available as equation number 3, and we have p square psi, which is available as equation number 2, and u is a certain parameter, and we have psi, which is available as equation number 1 above. Now if you feed all these parameters here, what do you get? You get this equation, which we have seen earlier. This equation is nothing but the Schrodinger wave equation. So let's analyze this further. So as you see that h bar is a constant, m is the mass, which is constant. Again, h bar is constant. I is under root of minus 1. So the parameters that we have here are psi. That's what we calculate. And then we have u, which is what we basically feed in, which is nothing but specific to the system that we are dealing with. So the u would always be different depending on the kind of system that we are dealing with. Now, of course, for our simplification, for our ease, we did a one-dimensional equation. If it's a three-dimensional equation, you have to replace this psi del square psi or d square psi by del square psi, which is nothing but the derivative with respect to all three coordinates. Now, often the question comes is that, how can you be sure that it applies to all cases? After all, it's just a derivation based on psi of a freely moving particle. And it's in fact not a derivation. I mean, if this is an equation which came out, and when Schrodinger gave this equation, he could not make much sense out of it. His explanation, if you read his work, his explanation was very different, and later on, people made some sense out of it, and they basically tried and tested on various different systems, and they found that it does apply to all cases, though there is no proof available. And that's why, Richard Feynman said, as I said earlier, that it's not possible to derive it from anything in this nature. It just came out of mind of Schrodinger. So let's look into this further. Let's try to use it in some of the aspects that we discussed earlier. We talked about this the constructive and the destructive interferences which are formed in the double slit experiment. Now, so let's say, what the experiment tells us is, if you have these two slits, let's say this is slit number 1 and this is slit number 2, and from slit number 1 you have some electron source, and slit number 2 you have some electron source, and if you turn on and turn off one of the slit at a time, what you get is you get psi mod square. So the psi mod square is nothing but basically the representation that you have a region in which the electrons are present, right? So let's look into this further. So we earlier talked about double slit experiment and the constructive and the destructive interferences being formed in the double slit experiment, and that was a signature of the wave nature of the particles. In this experiment, we had two slits. For instance, if you see, let's say if this is this screen which has these two slits, this is slit number 1 and this is slit number 2. And there are two electron sources. This is electron source number 1 and this is electron source number 2. Now, if you let's say switch off one of the slit, let's say we switch off this slit and we let the electrons pass through this slit, what you get is you get a pattern formed on the screen here, and that pattern will give you a representation where the electrons would have collided. For instance, in this case, this region basically tells that this is the region where the electron would have collided, which means this is the point where you get maximum number of electrons, and this is the point where you get lower number of electrons, and then it forms a Gaussian kind of a distribution as you move up or down. The same thing happens for the other slit. If you, let's say, close this one and open this slit, what you get is a pattern which looks very similar or same as the screen 1, and again in this case you get a Gaussian form. Now, if this was behaving precisely like a particle, then the probability of, or basically what you get at this screen, or let's say this is screen, when both the slits are open, would look something like this, where both the patterns are added together and you get something like this. However, what we saw was something like this, which shows some kind of constructive and destructive patterns being formed, and this can be explained very well from this the linearity and the superposition principle of these waves. The waves do follow this linearity and superposition principle, which means, so let's say you have two different wave functions. Let's say this is the wave function of the electrons which come out of slit number 1, and psi 2 is the wave function of the electrons which come out of the slit number 2. Now, collectively the wave function would be psi, and that is some amplitude a1 times psi 1 plus amplitude a2 times psi 2. Now, the probability of finding psi 1 would be nothing but psi 1 mod square, and the probability of finding particles through slit 2, which is nothing but the psi 2 mod square. Please correct this. Now, as we see, the probability of finding psi, which is psi mod square, which is the probability as p, as we can see that p is not equals to p1 plus p2, because let's say we take a simple case where psi equals to psi 1 plus psi 2, so the probability p would be nothing but psi 1 plus psi 2 mod whole square, which is psi 1 star plus psi 2 star times psi 1 plus psi 2, and if you simplify this, what you get is psi 1 star psi 1 plus psi 2 star psi 2 plus psi 1 star psi 2 plus psi 2 star psi 1. So psi 1 star psi 1 is P1 that we have seen earlier, psi 2 star psi 2 is P2 that we saw earlier, but we got these additional terms. Additional terms are psi 1 star psi 2 and psi 2 star psi 1. Now these additional terms are responsible for this constructive and the destructive interferences that we saw. If it was just P1 plus P2, then this P1 plus P2 would have resulted into something like this. But because of these additional terms, psi 1 star psi 2 plus psi 2 star psi 1, the overall function resulted something like this, which basically represent the constructive and the destructive interferences. So as you see, because of this wave associated with the particle, and when we represent this particle as a probability density function, which is basically the mod of psi square, gives you the probability of finding electrons, and this psi being a complex number would give you these constructive and destructive interferences mathematically as shown here. Okay, so let's stop here, and in the next class we will see how we can use or make use of the Schrodinger wave equation, what information we can extract out of psi for the quantum system that we are dealing with. And other than that, then we'll also look into some of these very basic problems where we will solve Schrodinger wave equation for various quantum mechanical scenarios, like particle in a box or particle in a finite or infinite potential well, or maybe a scattering of a free electron with a finite potential barrier, or the tunneling of particle through a potential barrier, and so on. So these are the things that we'll look into the next class, and we'll try to make some more sense out of the Schrodinger wave equation. Thank you.